Hello everyone, welcome to another devlog. So today we're going to go over this little PBR implementation that I've been working on over the past couple of weeks. So I wanted to make the spheres that we're rendering just look better. And PBR is something, so it stands for physically based rendering, if you didn't know what PBR stands for. And it basically per pixel you're doing kind of physically inspired calculations, like based on like where the lights are and how the sort of rough the surface is and if it's metal or plastic, basically. And it really improves the quality of how the rendering looks overall. So we're not really going to go for a realistic art style in this game, but something that you see in most games these days, if they don't go with a realistic art style, is they still have PBR just to make things physically look like plausible with like the lighting and that, but they will customize, they'll do some more post shading stuff to sort of make things look more like arty or something that's not realistic, right? So we'll probably do something like that afterwards, but I just wanted to make the overall primitives that we're rendering just look much better. So up here we've got a bunch of these little dials that we've been using to have a play around with the materials, and also the lighting and stuff. You can change the colors of these lights as well, and also their intensities. And also there's different little viewing options, which we'll go over more, where we can just view certain aspects of the PBR shader code and have a bit of a play around with the settings and see how it responds, just to make sure they are all correct. So yeah, let's get into PBR and how it works in the engine. So before we get into any of the implementation or the diagrams that I've drawn, I want to show all the places where I learned PBR from. So there's this really great video which goes over the sort of physics and maths of shading. So I won't be covering it in this detail. I want to provide more of this surface look and from a programmer's perspective. But I've watched this video like over 10 times and it's really great. I learn new things every time I watch it. Highly recommend watching this one. All the links will be down in the description. And there's this computer graphics tutorial by Victor Godin. This is what I used to sort of get the code up and running, and then I heavily refactored it afterwards. And you know, what sort of are the different formulas that I use today. So he's done the research there. There's also this blog post here, which is about image-based lighting, basically PBR as well. So if you're into reading, there's this blog post here. And also there's a Learn OpenGL1 as well, which I definitely looked into the image-based lighting section here, which is the cube map and things, and getting color from the cube maps. So speaking of cube maps, there's this other one here. This is where I got the cube maps from. The issue with these is they're not HDR. So when you do your you can't actually get proper lighting from this. You can have a value from 0 to 1. So you're just going to get color information, not necessarily any intensities. So, but it's still a good place just to start off with. So I've used this night one here and this daytime one here, but there's plenty more you can take a look at. So we just see that in the game right now. So you see here that these bright lights, they're not contributing to these, like this, as much as the sort of fake lights that we've got, which you can't really see in the sky because they're just saying, hey, there's light coming from a direction, and with PBR they sort of look like they exist up there. But yeah, right, so let's get into the details. Right, so we're going to talk about microfacets now, but I quickly just want to talk about these diagrams. So we have a title here to keep track of where we are, and on the right hand side there's a key, and this key you can obviously use to figure out what is on this diagram here. So microfacets are basically saying that, you know, you've got this flat surface in real life, and at a micro level it actually is not perfectly flat, depending on how rough the material actually is. So here you're seeing a perfectly flat surface, the light source is here, and it's shooting its rays out here. So when they hit the surface, they're perfectly reflecting. So if you increase the roughness here, you'll notice that the rays actually bounce off at a different angle. So again, this is at a micro level, and in computer graphics and for games especially, I guess, we do not model this microfacet explicitly. What we actually do is have some statistical maths, which will basically say, will give us, how much, what's the intensity of the light and how many sort of things are shadowing and other things which we'll get into in a bit. But yeah, we don't model these explicitly because if not, it'd be too computationally heavy. It's just done with statistics. So again, a key parameter here, which we just picked up on, is there's a roughness parameter for every material. And you see the things in the background, they're changing based on the roughness. We'll just take a quick look at those now. Okay, so we've got the close-up here of the spheres. So we're just going to go over the main parameters of PBR. So the first one is roughness. So as you saw, it creates that rougher surface. So rays aren't really going to perfectly reflect anymore. They're going to sort of come from all over when you're trying to shade a particular pixel, right? And then the other one is metalness. So on the left it's dielectric, on the right it's metal. So on the left basically non-metals. So the in-between is technically or physically not correct, but the math supports it, so you can do it if you want to. So see the roughness increase here for the metals, and as you see that perfect reflection, which we'll get into why there's more of a perfect reflection soon, kind of starts fading out and it gets more blurry and blurry until it's kind of just grayed out. So it's grey because obviously the surface color was grey, but you can obviously change these around and change the surface color too. Right, so let's get into the next diagram. Right, so with PBR and lighting in general, there's a thing known as diffuse lighting. So here's our sort of light source here, and here's the light rays, and they're going to hit this surface. You'll notice this surface is kind of see-through, if you will. And when the light hits the surface, it will bounce around these particles and sort of absorb color from that material. And then the light will eventually bounce back out into the camera. So this is known as sort of the diffuse lighting. So this only happens for non-metals or dielectrics. Metals do not sort of have any light that refracts around and reflects back into the camera, because the metals fully absorb light that refracts into the material itself. But they still have other ways of getting light from the surface, which we'll go into next. Right, so the other type of lighting to be aware of is the specular lighting. So this is where the light comes from the light source, hits the surface, and just reflects off. So it doesn't go into the material and come back out, it just reflects straight off the surface. So this is affected by the roughness as well. So obviously the microfacet will change. So it'll be a little bit more bumpy, so they won't always get the perfect reflection. So they can end up missing the camera as well if it's too bumpy. So with the metalness parameter here, what you'll notice is that when it's a sort of non-metal or dielectric, the reflected color would be gray. But when you have a metal surface, the reflected light will be the color of the surface. So it's just, this is something to keep note of. The color comes from the specular lighting for metals, whereas the color comes from diffuse lighting for dielectrics. So we're just going to see the spheres up close now and see the debug modes we have for those. Right, so for PBR, we have this nice sort of viewing modes where we can view individual aspects that contribute to the full PBR shading. So if we start on ambient, this is what comes from the cube map basically. So you need image-based lighting to get this look. So this contributes to every part of the sphere, even the parts which are not directly lit by the lights. So notice for dielectrics or non-metals, you're going to get this sort of color from the environment, whereas when you have something that's metal, you're not going to get any diffuse lighting. So ambient is a form of diffuse lighting. Whereas if we go over to the reflected view mode here, this is specular lighting, and we're just going to make the albedo a bit red. And you'll notice here for non-metals or dielectrics, this did not change at all. But as we make it metal, you see the red has already came out in the color. So now we're going to go to the direct lighting diffuse. So for non-metals or dielectrics, you're going to get the color from this diffuse. Sorry, the color of the surface from the diffuse lighting. And if we make it metal, you'll see how the color just goes. So there's no diffuse lighting for metals. Right, so we go to the specular lighting now from the direct light. For non-metals or dielectrics, it's going to reflect the color of the light, and it's not going to get tinted by the surface at all, which is a little bit red. And when we make it metal, you'll see how the reflected light gets colored by the surface. Right, something to be aware about when you're doing PBR is that we don't actually trace every single ray from the light source. And you've seen in the current or the previous diagrams is they've come from the light source and they just happen to go into the camera. I guess you could probably do it this way, but it's just a bit easier if you trace the rays from the actual camera themselves. So the renderer could be just a rasterizer, and you just take a ray from the rasterized pixel from the camera. And this green box here is meant to be the sort of area of the pixel that we are kind of shading. But it's not to scale or anything. So you'll use essentially the vectors. You'll use a bunch of different vectors and calculate a type of, you would statistically work out all those light rays that could possibly hit this area and how many of them are going to go back into the camera itself. So we'll just dig into that more specifically now. So one of the key pieces of maths inside this PBR code is something known as the BRDF. So it stands for the bidirectional reflectance distribution function. It sounds a bit scary when you first hear it, but it's kind of simple when you break it down. There's this bidirectional part, which is basically saying there's two key vectors, there's two key directions. There's the direction to the light source that you're trying to calculate how the color, or what color is coming from that light source into this pixel that we're trying to light. So these are the two vectors, the light direction and the view direction. So you should calculate this BRDF technically for every single direction that light is coming from. And there's also the surface normal as well here. And another key vector as well is this half direction, which is calculated by adding the light direction and the view direction together and then normalizing it again. That gets you your halfway vector, which we'll see how that plays into the PBR code in a bit. And also, if you remember from a light source, there's two things that can possibly contribute to the color. It's that diffuse and that specular lighting term, right? So keep that in mind when we go over these next set of things. Right, so the first one we're going to look into is this thing called the normal distribution function. We've got the debug viewing mode here, so we're just seeing how that contributes to the lighting for these spheres. And what you'll find is that this is a thing that contributes to the specular term because it's the reflectant, stuff that perfectly reflects off the sphere surface itself. So remember, you know, if we change the roughness here, the surface will get rougher, the microfacet will get rougher, so therefore that perfect reflection of that light is not really going to, you know, it will get bigger and bigger, and then eventually it will just sort of average out over the whole surface of the object. But I think my light is actually very intense, so really we should bring that down a bit and see it in action again. So we increase that roughness here. It's really just grays out there like that, and that blue light is really intense. So we do it one more time. There we go. Right, so here we're going to take a look at the diagram version so we can see it from another perspective. So here's the value of that, which comes from that normal distribution function in the code. So we have like 0 roughness here, and that specular highlight is going to be like really small, right? But as we increase the roughness, that specular highlight gets bigger, right? So here you see this number really jump up, and then as the roughness increases, you'll see here how the rays are going outside the pixels, so they're not contributing to the for this pixel anymore, and essentially it just averages out. It will average out all over the surface, something like this, where you have like, essentially you're saying like, I don't know, here we model it as a ray, but yeah, it's not as dense as it was earlier, right? So if we move around this pixel here, we're going to see it differently. So let's just watch it one more time. So we increase the roughness, it really goes up and gets very sort of dense there, and then the denseness just sort of spreads out over the whole surface of the object a bit. So we're going to move this pixel and see that in action. Right, so we've moved the pixel a bit to the left now, so we can see a different angle with the normal distribution function. So if we increase the roughness here, so there's just like, you know, a tiny little amount that's contributing. So there's still a ray here, I guess, but it's so small that you won't be able to really see it contribute. But as you increase, it goes up to something that's more measurable, like 2 here, and then it will drop down something smaller. So it's way smaller than it was over here. Up in the middle it was getting like 23 or whatever. And the reason is because, well, it was getting 23 at the peak, whereas it's getting 2.5 at peak. And the reason is because you've got this normal vector and this half vector. So the closer these are together, the more effective the normal distribution function is. So this would mean that the closer, when these things are exactly the same, you're getting that perfect reflection from the light source into the camera. So that's very obvious, right, when we talk about normal distribution, because, you know, it is basically the reflection into the camera. So yeah, that's just the way it is done with the vectors and things, which you'll see more in the code in a bit. There's another part of the specular term here, which is called the geometry shadowing function. So this gets combined with that normal distribution function, and, you know, the rougher a material gets, the more of it sort of like shadows, the more darker it kind of gets. So you notice here it goes from like 1 here to 0, and that's for a perfect reflection ray, which you'll see in a bit in the diagram. But also it contributes things that are not perfect reflections more. So the way this one works is that there's the microfacet, and you've got these hills, and essentially these hills or these bumps can essentially, you can get some shadowing, so they will sort of like shadow from the light's perspective, or they will mask from the camera's perspective. So they can actually, reflected rays can get blocked by another microfacet edge, if you will, from a little hill. So we're going to take a look at that diagram now. Right, so this is the diagram for the geometry shadowing function. And, you know, imagine there's a bunch of rays coming from the light source, and this is the pixel that we're trying to color. So we've just got a ray coming from the camera here, and we're working out statistically how many of these rays that cover this, how much of the light that covers this sort of area, like how much of it actually ends up not getting blocked by the little hills in the microfacet which could block incoming light from the actual light source, or the reflected light. When it reflects, it could accidentally bump into another part of the microfacet, and then it wouldn't reach the camera anymore. So with zero roughness, you'll get that perfect reflection. There'll be no, there'll be no hills that'll be blocking the light at all. But as you increase the roughness, you'll start to get light being blocked from either end, and to the point where it'll just be a smaller amount that will contribute. So essentially it's just another scalar value that multiplies alongside with that normal distribution side of things. And the thing that the vectors that are used in this formula is the normal vector, and the vector towards the light source, and the vector towards the camera as well. So these are the three things that help work out this geometry shadowing function. Okay, so here's another look at the geometry shadowing. I've moved the pixel a little bit to the left, so you'll notice that this sun, the direction towards the actual light source itself is actually closer to the surface normal. So you're going to get less shadowing from the light angle, right? So these rays are more likely to bounce into the camera and not get shadowed. But if the camera goes more perpendicular to the surface normal, it's actually going to get more masking. So less of the rays that bounce off into the camera are actually going to contribute in the end. So see here, as it goes down, the amount of rays that contribute just goes further down, and that's with a very rough surface. If I take the roughness back up here, you get that perfect reflections. Therefore, there's not going to be any microfacet hills. But yeah, so as you increase it, the more likely it will. The more of the value will actually go down. Right. So the final part of the specular BRDF is something known as the Fresnel function. This is actually, it's multiplied with the normal distribution and the geometry shadowing, right? And you'll see here how it's actually got 3 channels instead of the 1 channel. And this is because there's actually a color that comes from here. And you see there's no color coming from it right now because we are currently on a non-metal or dielectric. If we increase the metal, what you'll notice is that the red color is coming from that surface, the surface color of the color of the surface. So this is where the term which brings the color into that specular lighting. Right, so here's the diagram with the Fresnel. What you'll notice is that the sun is or the light source is closer to the ground, and the rays coming out here. And our camera is going closer to the ground and then far away from the ground. As it gets further away, it gets weaker. The Fresnel is weaker. As it gets closer to the surface, it gets stronger. And how the maths works is you got that halfway vector, which we see again, and then you have that view direction, right? It takes the dot product between those two. The more perpendicular those guys are, the stronger the Fresnel is. So if we increase the metalness, this is dielectrics, you'll notice that it's actually grey for dielectrics. But as we increase it, the color really shows through, and the intensity also goes up as well. So what Fresnel basically is as you get closer to the ground, and the sun and the camera get closer to the ground, the more the reflected light is actually, or the stronger the reflected light actually is. Okay, so I've got this view mode here called light, and this is only showing the lighting that's coming from the direct lights, none of the image-based lighting cube map stuff. And this is what we're going to see the code for in a second. So this is for the plastics or the non-metals, right? The dielectrics. If we move up the metalness, you'll see here how you're not getting any other sort of surface color appearing. So all of the other lighting really actually comes from the environment. So yeah, it's a key thing to take note. These direct lights do not actually contribute a lot to the metals. If you want to have good looking metals, you need to have image-based lighting in, which we'll look into in a bit. Right, so the first thing we'll take a look at is a couple of structures that we pass around in the shaders. So it makes it easier that rather than having these massive function prototypes, we can just pass around a few structures and all the information, all the data is in there. So we have these input parameters in the shading strut, which is the view direction. So it's the normalized vector to that pixel on the camera that you're trying to shade. You've then got the surface position, so the position in world space for the surface that you're trying to color in. You have the surface normal, so yeah, the normal of the surface at that pixel. And you have this thing called F0, which is calculated internally, which we'll see in just a bit. And the surface normal dotted with the view direction. So it's actually dot product of surface normal view direction, and we max out. We have to take the maximum value between 0 and that dot product, because the dot product can return negative values, and we don't want negative values in our lighting. The next structure is this lighting strut, which has a couple of input parameters, which is the radiance or the color, and the intensity of the light combined into one. And then we have the direction of the light in world space. And the final structure that we pass around is the material itself. This one has a vector 3 with the albedo. That's the color of the surface. We have a vector 3 for emissive. We have a float for roughness and a float for metalness. These values are between 0 and 1. So we have a function called calculate surface color. So per pixel, when you're trying to shade, we fill in those shading data structures. So shading and material rather. And then we call calculate surface color, and this will just return a color that we will then output to the screen. So we calculate the F0. This is part of that Fresnel equation, which you'll see the implementation of soon. But basically for metals you want albedo, whereas for the non-metals you basically want a very dim sort of gray. So basically we just lerp from 0.04. So there's actually some maths behind this, which I advise you look at those other videos I've referenced. They really go over this in more detail. But yeah, 0.04 is that sort of default color for dielectrics. They actually vary just a tiny bit, but you can just default to 0.4. It's something to look into the future, I think, for me. And then we've got the albedo here, and basically if it's metal, we want albedo. If it's not metal, we want this sort of very dim gray electric color. Then we calculate our normal dot view, which we saw earlier. And now the next thing to keep an eye out on is the ambient and reflected stuff. We'll look at this in just a bit. But the thing I wanted to pay attention to is the lighting that comes directly from the light primitives in the game. So we only have 2 lights right now. You saw one was moving and was cyan, and the other one was kind of just white. So we have this light radiance, and we're going to go over all of our lights, and we're going to accumulate this light radiance here. So we make this lighting structure. We take that light color and we multiply it by the intensity, and this is the radiance of the light itself. The radiance coming from the light and the direction of the lights as well. So we pass these 3 shading, material, and lighting into the calculated light radiance, and this is where the BRDF and all that is calculated. But here's our switch statement for our different view modes, and then basically at the end we take all of the radiance from all the different places, all different light sources basically. So you got that light radiance from those direct lights, and the material emissive, the albedo radiance, which we'll look into in a bit, and the reflective radiance, which we'll look into in a bit too. And we return that accumulated radiance, and that's the final surface color. Okay, so this is the calculate light radiance function. It just returns how much of the radiance, or it returns the radiance which is going in the direction of the camera to that pixel you're trying to shade. So at the start we calculate that half direction which we saw earlier, and all those different vectors that we have, like that half direction, surface normal, light direction, and the view direction, we calculate some dot products between some of those because they are used inside the BRDF formulas, which you'll see in a bit. So one of the sort of inputs to these formulas is this thing called alpha, and that is basically just roughness squared. So you just compute that here. Then we calculate the Fresnel using the Fresnel-Schlick equation, which you'll see the implementation in a bit. We pass in the F0, the view normal dotted with the half direction, and we pass in the roughness too because that also affects the Fresnel. And we get the result here. So remember, you get some color in here if it's metal, but you get kind of gray if it's not a metal. Then we basically we do one take the Fresnel here, and we multiply with one take the metalness. So basically you're saying how much diffuse light is going to contribute to is actually going to contribute to this surface color. So the more the Fresnel is, the less diffuse light that's going to be contributed. The less Fresnel, the more diffuse light. But obviously if it's metal, you don't get any diffuse whatsoever. So the diffuse part of the BRDF is actually really simple. It's known as the Lambert term, I guess, or function. Basically, you just divide the albedo by pi, and then you just multiply KD by Lambert. And that is basically diffuse for a direct light source. And then the specular is calculated using this Cook-Torrance equation. We'll dive into the implementation in a bit, but there is actually, the thing is about the BRDF is it's built to be this flexible, well, kind of, there's a bunch of different implementations of the specular term, and also the diffuse as well, I guess. So there's actually other methods online that people have come up with. But I'm just using the ones which are basically popular these days. So yeah, you can always research into that as well. So then the BRDF is basically just the sum, or you just add diffuse and specular together. And then this BRDF is multiplied with the lighting radiance. So remember, that was the light color times by the intensity. And so that'll get you basically the color, and then you need to make sure that you multiply this with the normal dotted with the light direction, because if not, you're going to get the parts which are in shadow to the light, so they're sort of behind. They're pointing away. The surface that's pointing away from the light is going to get colored if you don't have this. So this is why you need this in here. So this is that Cook-Torrance specular term here for the BRDF. And remember, there is different ones, but we're using this one because I think it's kind of popular these days. So the Fresnel comes in here because the Fresnel is part of that specular BRDF. Remember, it gets multiplied with the geometry shadowing and the normal distribution function. We're using the Smith geometry shadowing function and the GGX Trowbridge rates. So if you Google these, you can find the mass formulas online or in those videos and articles I've referenced. So yeah, the alpha and the dot products between those four important vectors are passed in here, and we pass these into the geometry shadowing and Trowbridge rates functions. So then we also calculate the denominator, which is like this 4 multiplied by these vectors here, and you have to make sure this here is maxed with a small value, so it's not 0, because otherwise you're going to get a divide by 0, and then just things won't look right when you have certain conditions. So let's take a look at those the individual specular terms for this Cook torrents. Right, so this is the normal distribution function that GGX Trowbridge writes. It just does that nice specular highlight, right? I'm not going to go too much over the details, but the more when it's a perfect reflection, you're going to get that nice dot that appears, and the closer you are to that perfect reflection, the more as it gets rougher, it will start to appear on that pixel. But when you're far away from that perfect reflection, you'll only get color when the roughness is kind of gets higher, right? And it just averages out across the surface towards the end. With the geometry shadowing, use the Schlick Beckman GGX, and this passes in an alpha with an n.x, x meaning something else, because it actually is used twice. Because remember, from the shadowing function, there's two directions that it comes from, right? There's the shadowing, which is the direction from the light, right, with the normal. So the closer those normals are together, or the more in the same direction those are together, the less shadowing that's going to happen. But the more perpendicular they are, the more shadowing that's going to happen. Then you multiply the result of that, with the normal dot view. So this is the masking. So when the light reflects off the surface, how much does that, the more perpendicular they are, the more masking that's going to happen. So the more chance the reflected ray is actually going to bump into another part of the microfacet and not reach the light. So yeah, this just basically calculates some probability of all those rays that are in that pixel, how many of them are going to get, how many of them are going to not get shadowed or masked. Right, and the final one is that Fresnel Schlick. So it's the Schlick version of the Fresnel term we're using. So you pass in the F0 the dot product of two vectors, right? It could be, because it's used in two different ways in the overall PBR lighting, which you'll see the second one soon, and some roughness as well. So this is the one which has been modified with roughness. You will see a version without this. So I'm not going to go too much over the details again, but the more perpendicular that the two vectors are, the more the stronger the Fresnel is, right? The less the less perpendicular they are, the less the Fresnel is, right? I remember this is F0 is going to have more of like a color if it's metal, but if it's non-metal, you're just going to get a gray, right? A very dim gray that comes in here. Right, so we're looking back at that calculate surface color again. So this is the entry point of everything that we've seen. So we looked at the direct lighting. So you're just going to see the lighting that comes from the direct lights. So it's going to look mostly okay for the plastics, except for there's going to be a dark side because you've got the normal dot light direction, and so you would not see anything that's not directly lit. And then if you move over to being a metal, then you're just going to see basically the normal distribution function. You're not going to see any sort of like surface color at all. So that really all comes from the reflected light, because again, the metals only show reflected light, they don't show any diffuse light. So direct lights will only give you that sort of the light that comes directly from the light primitives itself. So what we actually need is the lighting which comes from the rest of the environment. So we have a cube map, which is seen in the background, and this cube map is kind of the rest of the environment. You can do some more computationally expensive things later, but for now you can just do image-based lighting and it just gets you up and running, and you can tweak it more later on. So there's two key aspects. There's the ambient radiance and there's the reflective radiance. Ambient is diffuse, whereas reflected is specular. So we need to do a Fresnel here. We pass in the F0 and the n dot view, so normal dot view direction, and we use the normal here instead of the half direction because the normal is the half direction when you have in terms of a reflected ray, right? When you're reflecting the view direction on the surface normal, you are going to get, and the light that comes from the reflected ray, those two added together and normalized gives you the half direction. So what we have here is we calculate that KD, which is the amount of diffused light that's going to contribute to this pixel here, because if it's on the edge, you want more of that Fresnel, which is more of the reflected radiance rather than the ambient radiance, right? Which you'll see in a bit. So basically, we have a pre-computed cube map, which has all of that ambient radiance stored in there. So all we need to do is just use the surface normal just to simply look it up. So it gets stuff from the cube map, but not necessarily stuff it's directly neighboring things. So if you want stuff to be really correct, you need a more complicated solution. But for now, this will do. And then we take that irradiance. So irradiance means it's the amount of light that comes from all around, whereas radiance means it's the amount of light that comes from a specific direction. So we'll see more about that in a second in a nice diagram. And then you multiply the albedo of the surface by the irradiance, and that should diffuse. You just multiply the diffuse by the KD, and that is your ambient radiance. So let's take a look at the diagram for the ambient radiance now. Right, so we have another diagram here which is showing how a cube map is constructed. So this cube map is a much lower resolution, and this stores the irradiance for a given normal. So basically, you know, cube map can be thought as something which is like infinitely far away. You can also you can move around inside cube maps and that, but we don't really do that. And also you could probably like blend between a couple of cube maps or whatever. But again, we're just keeping it simple, and we're just imagining that for every single time we hit a surface and we get a surface normal, we're just going to imagine they all point in the exact same direction and hit the cube map in the same place. So with this ambient diffuse color, the way you need to produce it basically is you need to shoot a ray. So you take your surface normal and you shoot a bunch of rays around the hemisphere. So you don't shoot them under the hemisphere, because that's going to be where the surface is, and you know you're not going to get any rays that come under and then reflect into your view direction. So basically, we pre-compute a cube map where for each pixel here, so we've seen this pixel here, we are taking the normal towards that pixel we're trying to shade in. We shoot rays all around, and we sample the big environment map, the one that you're seeing in the background here. And you get all the samples, you take the average, and then you store that in this pixel. So the next time, so when you look at this pixel inside the PBR shader, which we just saw that ambient radiance, right, or that irradiance, we simply just look it up, and that's a pre-computed value of all the irradiance. So let's take a look at the view debug mode again and see how it looks. Right, so here's the ambient color. So because it's a very dark scene, we're going to have very dark colors, but you'll notice that it is kind of a little bit brighter underneath, maybe because of those other lights, and maybe it's a little bit darker on top. So we can actually open this up in the screenshot viewer and see that a bit more. So let's do that now. Right, so here's the screenshot viewer. So we're going to increase or decrease the white levels, and you'll see here how it's brighter here but darker on top. So this is what the irradiance map texture looks like inside our texture viewer. So we have 6 layers, right, one for each face of the cube map. So we're just going to cycle through those now. You see they're a little bit different. This one looks like the top, it's darker, right? And yeah, so there's just a bunch of different layers. And remember, it's much smaller resolution. This one is 32 by 32 pixels, whereas the environment map is actually 2K per dimension. Right, so here's the dark patch here that I'm talking about. When we then apply all of it on, right, you'll see that you get the ambient color, but it's also using the reflected, which we haven't covered, but we'll be doing that in a second. Right, so we're actually using the Diffuse Irradiance tutorial from the Learn OpenGL website. This is the one that I actually used to get this up and running. So hopefully that diagram that I showed just gives you a good basic idea of how, you know, to approach this thing. And then I also use the Specular IBL as well, which is for the reflected ray, which you'll see in just a second. Oh, and also that blog post that I shared as well, the image-based line with multiple scattering, also covers that diffuse and specular one in a slightly different way. So I highly recommend you read through this as well and look at the image-based lighting section here. Right, so the final part of this surface color that we didn't go over is the reflected radiance. So this is that specular contribution from the rest of the environment that's not the direct lights. So you calculate the reflected ray direction using the reflect function. You have one in GLSL, you have one in HLSL, I think. If not, there's maths out on the internet. Find the maths and use that. It's the negated view direction. So remember, the view direction is towards the camera. So it's the opposite of that. It's towards the surface instead. And the surface normal, and that will get you the direction in which it's reflected. Like a perfect reflection. And then we sample from the BRDF texture, which stores an average of a BRDF that's been pre-computed. That's in the tutorials for the OpenGL stuff, which you'll see, or the Learn OpenGL tutorial. And then there's the reflected radiance, which comes from another cube map. This one is the same resolution as the actual cube map environment, but it's a different one called a pre-filter map. I might change this name later. I'm not really a big fan of the name, but yeah, it's called a pre-filter map. It's another cube map, and you sample it with the reflected direction. And then it has a bunch of different MIP levels based on the roughness. So as you increase the roughness, you want to get a blurrier reflection, because you're not going to get your rays perfectly reflected. You're actually going to get more, a lot of those rays which come from the light source are going to be, or the environment in general, are going to be bounced at different angles, not perfect reflection. So you just basically storing a pre-computed version of that in that cube map, which we'll see the texture viewer and the game in a second. And then you take that Fresnel that we source how much specular light is being contributed to this pixel, and it also has a bit of color in there as well if it's metal. And we multiply it by this BRDF X, and then we add the BRDF Y. Again, don't be too worried that you don't know much about it. It's all in the blog post and the blog post that I've linked. And then we multiply that BRDF. So it's just another bidirectional reflectance function, which we saw in direct lighting, but just here. And then we multiply it with the reflected radiance. So let's take a look at the scene and just see how this contributes to the picture. Right, so here's the reflected view mode. So we're just seeing purely what the reflected view ray gives. So remember, every pixel we shoot has a surface normal, and we reflect the ray, and we sample from that new cube map called the pre-filter map. And it has MIP levels based on roughness, which we'll see in a bit. But remember when we had that Fresnel term, and that Fresnel term, when it is a dielectric, it has like a 0.04 color, doesn't it? So it's not going to get that strong of a reflected color. But the more metal it is, the more reflected color it's going to get, right? And just to have a bit of a look at the Fresnel, this is the Fresnel term for that reflected ray. You'll see here how it's brighter around the edges, right? So it's more brighter around the edges here. And when we look at overall, you'll see here that you get this nice, like strong reflectance around the edges. And that's purely comes from that reflected ray and reflected specular and that's thanks to the Fresnel. So let's take a look at the diagram and then the cube map. Right, so this cube map is the same resolution. So it's not a smaller resolution like the diffuse one. This specular, this reflected cube map is the exact same resolution as the environment map. And it works in a very similar way, how we have a pixel and then we have this normal vector, which is just from the middle of the environment. So every time we have a reflected ray which just goes in that direction, we just use that. We just take this pixel, which has all the pre-calculated reflected information in there. So when we have a roughness of basically zero, we just shoot a bunch of rays going forward, and we average the color out from the environment map, and then we store it in that pixel there. And then as you increase the roughness, these rays get wider and wider and wider to the point where it basically becomes like a hemisphere, right? A little hemisphere. So let's take a look what that looks like when you have your pre-filtered map in our texture viewer. So here's what a pre-filtered map looks like. So it uses this thing called importance sampling. So you don't really get like a sort of downsampled looking image. You get a really nice blurred image. And it's kind of interesting how this is at zero roughness, right? This is the MIP level at zero roughness. It's kind of interesting how that reflected ray still kind of looks like a perfect mirror, even when you have a little bit of roughness. Yeah, and the MIP 0 kind of looks like this. So let's just increase the MIPs. This gets blurrier and blurrier and blurrier. So as the surface gets rougher, we are going to sample between two different MIP levels and it will interpolate for us, right? That's how the sample code works for GPUs. But it gets rougher and rougher and rougher basically. And obviously lower resolution. So let's take a look at some of the code, I think, and just so you guys can have a reference to how my code works compared to the tutorials. Right, so here's the render irradiance map. We're using a compute shader, so just launching per pixel, and per pixel of a cube map face, and we launch this shader for every single face of a cube map. And basically, we get a normal, right, towards the pixel that we're trying to render into this frame. So it's from the center of that cube map. And then, you know, all this code basically comes from the Learn OpenGL stuff and that blog post as well. And this is just the for loop that computes the hemisphere. So we're doing, I think it's, yeah, we're doing like thousands of rays per, you're doing thousands of rays per pixel over the hemisphere. And then we're counting how many rays, and we're accumulating the irradiance. And then at the end, we just essentially work out the average of that irradiance and then store it inside the texture at that coordinate. It's all cached, so we don't have to do all of this calculation per pixel. So yeah, we're just sampling the environment map at MIP 0, like so. And something to be aware of is, since this is a low resolution resolution version of the environment map, we actually, you know, you got to make sure you get your faces right, because it's really easy to sample the wrong face and store in the wrong face. So one nice bit of debugging thing you can do is just output like a low resolution version of the environment map and just make sure your key map faces are in the right place, basically. Right, so let's take a look at that pre-filter map. This one is a little bit more involved. It does some thing called importance sampling, but again, the same sort of debug thing applies. Make sure you got your faces set up in the right direction with that by just reading from the cube map and then putting it into the new cube map. But it's a similar sort of thing where we have a normal going towards the pixel that we're trying to render this frame. So yeah, we launch a compute shader the exact same way, but it's a bigger cube map this time that we're rendering to. So it's more expensive. So you just take a normal from the center of that cube map to the pixel that we're trying to render for. And again, I'm not going too much into the details again, but there's a number of samples. There's a number of samples basically, and how rough, depending on how rough it is, depending on how more spread out those samples are. And then that is all worked out based on this like important sampling thing, and all that code is available on the on those blog sites there. And another key thing to take note is that this pre-fill map shader is also launched per MIP level, because there's a MIP level for each roughness as well. Right, so one thing to take note is, if you remember that this sort of specular pre-filter map thing, that reflectance map that we saw, that MIP 0 was really blurry. And if you see here, this is at basically roughness 0. It is a little bit blurry, but it's not like super blurry. So the reason why, so I think I've tweaked my numbers a little bit. So I've made the base MIP a little bit more blurrier, because for this game, I want it to be sort of more zoomed out. And when I was more zoomed out, I was getting some very jumpy pixels, like things were just bright and then not bright, and it was causing a lot of flickering. But now, because I've increased that roughness just a little bit for MIP 0, you're still seeing it reflected at this distance, but you're not getting it like flickering and causing these really jarring like artifacts. So it's really something you should play around with when you implement it in yours. But you can always just make it a little bit rougher. Because I'm doing ray tracing, it's hard to get the derivative. Maybe you could just increase the roughness based on the between 2 pixels. What's the difference between between something like the UV or something like this, and use that to calculate the roughness perhaps. But yeah, it's something we're gonna play around with in the future, I think. Right, so actually I got a bit interested in looking at what different diffuse models there are, and there's actually this one called the Oren Nayar diffuse calculation, which is different from the Lambert one. Lambert is just albedo divided by pi. It's dead simple, but it's nice and quick, easy to compute, but it doesn't look as good as it can. So there's some more sort of physically based ones. So I got this implementation from the internet somewhere. This is one that I tried, and it just ended up looking quite nice. There are some other ones out there which were different, so I'm a bit on the edge if this one is correct. But in the future I'll look at it and more in depth. But I just thought I want to show how this actually looks and how it compares. So the thing that's different about it to Lambert as well is it also takes the roughness into account, and so it will change as the roughness increases or decreases. The way I compare it side by side, if you will, is we just have this, that roughness slider that we've got. When it's 0, it just does Lambert, and for all the others, it does the Oren Nayar. So let's go and see how that looks now. Okay, so this is us viewing the final fully shaded thing. Bearing in mind, I've not applied the Oren Nayar to any of the ambient irradiance map yet. That's something that's still got to come on. But just, you can already tell with the direct lighting. I'm just gonna get rid of the blue light because it's kind of annoying. But you'll see here, as soon as we switch from Lambert here to Oren Nayar, it's already it just feels a lot softer and subtle, right? And as we increase the roughness, the diffuse changes a bit, I guess. But if you really want to see it, we've got to look at the debug view mode. So here's the direct lighting diffuse. So here's the Lambert. Here's the Oren Nayar, and as we increase it, it sort of gets a little bit brighter up here, right? So I'm just going to monkey around with that a bit. Right, thank you so much for watching this devlog, guys. So this is devlog 13, day 120 to 125. You can view those on the VOD channel if you want to see it more in depth of me trying to figure out PBR and the steps I sort of took along the way. But also, if you want to get access to the source code, you can subscribe via Twitch or Ko-Fi. Ko-Fi is much better for me. More of the monies goes in my direction. But the source code would be very useful if you're interested in playing around with the repo and, you know, maybe I didn't quite cover it in the detail where you might have a question around, and you'll be able to sort of have a play around in the code base and see for yourself what, you know, what the answer is basically. And yeah, so thank you for everyone who's supporting me there and doing so already. Really appreciate it. There's a VOD channel on YouTube. You can check that one out and see the VODs, any past VODs. Got lots of cool stuff on there. And there's a Discord if you're going to come and hang around in the meantime. Right, thank you guys. See you in the next one.